So in the previous video, we covered the electric potential at point A, where point A is plus 4 meters, and point B, where B is plus 2 meters. And this one, we're going to find the potential at A, where A is a positive 2 and B is a minus 4 along this z-axis. Okay. Now, part A looked like this, where we set up the integral, but part B is going to be a little bit more tricky. So let's set up that integral for part B, where we have potential A with respect to B, and point A is going to be z at 2, and point B is z at minus 4. And we can keep this in the Cartesian coordinates, very similar to this one, but we're going to have to break this up because, recall, in the first video, we determined that we could rewrite in Cartesian coordinates so long as we broke up our electric field into these two parts when z is larger than 0 or z is less than 0. So this means that we would need to break this integral up. 1 for the negative part and 1 for the positive part. Okay, now if we do that and substitute in for our fields on the negative one, our field is minus. So we have the minus and we're going to have to find some dl, whereas in this part we have minus z hat dot with dl. Now, if we are to go further on this, we need to determine what the dl is, and this time it's going to be a little bit more tricky. So in the first part, we said that the dl went from here to here, and in this case, right, we can make the dl go all the way from some minus, where z is equal to minus 4. We can take that dl as z dot dz for the entire thing. So now we can take a path that goes from minus 4 to our point B at plus 2. And so that dl is going to be z hat dz for each case. So our field is different here, but the dl we can remain the same because the dl is pointed up from point minus 4 to 0 for each case. All right, so now we just need to substitute that in. And I'm going to advise you now of one more thing that is actually going to make this problem a little bit easier, which is that we should also, in fact, break this integral up into two different parts. So let's keep that, the positive part, but let's break this one into two parts. One goes from minus 4 to minus 2. And the other goes from minus 2 to 0 when 0 is approaching it from the negative side. And this one goes from 0 to 2. Okay, so now the reason that we may want to break that up is because we can start to simplify this a little bit. And we can see that these two are going to give us some tricky situations because we're trying to evaluate at a point 0 where we're going to have 18 over a 0. So this is going to give us some infinite number. And so if we break these two up, we can see that these two are going to cancel with each other. Now, I'm not going to give a detailed mathematical explanation of this, but instead let's look at this visually, where we can see that if this is along the z-axis and this is our field strength, we can see for this one on the left side here that this one is positive, and so the approximate function may look something like this, where it's approaching infinity at z equals 0. Now on this side, we can see that it's negative of that same function, where at 0, it's approaching minus infinity. And so if we're integrating from z equals minus 2 to z equals 2, we can visually see that this area and this area are going to cancel out. So these two integrals are in fact going to cancel for us, and we would only need to do this one integral from minus 4 to minus 2. So that means that we can actually simplify this as this minus 4 to minus 2 of 18 this now when we evaluate this, we get there are a lot of minus signs here. However, simplifies to 18 over 2 minus 18 over 4, or 9/2, or 4.5 volts is equal to VA VB. And now that was all due to canceling these two things out, and we were able to cancel that because we did this integral in Cartesian coordinates, where we were taking the dl along the dz. Now the question that we're probably asking is, why can't we just use the spherical coordinate system here and perform this problem similarly? Now there's a pitfall here that may not be exactly obvious if we do this in the spherical coordinate systems. So let's try to look at what this might look like if we were doing it in the spherical coordinate system. So I'm going to take this and let's look at what the path might be. So we would want to take a path from minus 4 to plus 2, right? This would be the path on the spherical coordinate side. Now if we were to stick in the spherical coordinate systems and just try to do an integral, so let's say, oh well, we realize that radius is equal to 4 here, radius is equal to 0 here, radius is equal to 2 here, radius is equal to 4 here. So let's just say, well, let's integrate from radius of 4 to radius of 2. Okay, so what does that actually end up being? Well, the path that you inadvertently would take is a path from radius 4 to radius of 2. So if we were to write a path from radius 4 to radius of 2, right, we were taking this r dr, like this, and we think that we're going in this direction, but this path is positive, is actually pointed in the positive direction. And so the mistake that we made is that the path pointed from 4 to 2, that you would make is that the path points from 4 to 2, and so you're going to end up with a difference in your minus sign. So let's take a look at that. So if we go from 4 to 2, this is the path. We have our field, 18 over r squared. Like this. Okay, so now we perform this integral, and it's going to, and it's, minus e dot dl. Now, when we perform this integral, what we get is 18 over r, because we have a minus sign that cancels, from 2 to 4. And when we solve for this, what we get is minus 9/2 is equal to minus 4.5 volts. So the mistake that you likely are going to make if you stay in spherical coordinates is that the path needs to be pointed down here, but if you just select this r hat dr, this is actually a path that's pointed upwards, right? This is a path that's pointed outwards on the z-axis. So in our coordinate system, we need to be looking at the difference between the two. But if you just think to yourself, oh, I can do the path from 4 to 2, that doesn't actually go from 4 to 2 because your path is in the wrong direction. Right, this path is positive, but really we would need to make that path negative. And so if we were to change that, we can see that if this path had been negative, then these two things would actually cancel out, and you'd have a negative here, which would make this positive and this positive, and you would get this same positive 4.5 volt result. So either way this problem works, you're either going to need to be careful with your differential length when doing the integral in spherical coordinates and make sure that you add in this negative to account for the path that you've taken, or you should do it in Cartesian coordinates and perform some sort of cancellation operation where you keep the path in that same direction and follow the path naturally. So sometimes it's easy to look at these integrals in Cartesian coordinates because the path may be a bit more natural. However, you can also solve this in spherical coordinates if you are careful with your differential length to account for the fact that taking the potential from 4 to 2 is going to require you to add in a negative sign here in order to get that correct path from a radius of 4 to a radius of 2, rather than just accidentally or blindly assuming that the path you take is this. It's actually going to be minus r hat dr. Okay, so thank you for following these videos. Hopefully this helps you understand how to perform some of these path integrals, and I'll see you in the next video.